We're here with another person who's willing to talk calculus with us. We usually start off by having our guests introduce themselves. So,
I'm Maya. I'm in 10th grade, and I'm a math lover, non-professionally, as of now.
Yeah, and she was willing to share with us one of her favorite bits of calculus.
That's great.
So I usually ask people what do they want to talk about, and you had something in particular.
Yeah, I wanted to kind of show a proof that I'd seen for Euler's formula, e to the pi I plus 1 equals 0, using Maclaurin series. In that case, should we just get started with the proof?
Sure. So, as you were saying with Euler's formula, right, it's this kind of simple...
It's very simple, and it's kind of idolized in the math community a bit as like the most beautiful formula because it has e, pi, I, 1, and 0 all together, and it's not some crazy long 12-page thing that has to like reconcile them all. And you know, E is cool because it's got a lot of, as you probably know by now, a lot of power in calculus. Pi, of course, is a very famous number. It shows up in a lot of places. I is the imaginary number. And then 1 is the multiplicative identity, and 0 is the additive identity. So they're all just kind of really important numbers, and they all play together pretty smoothly in this.
So my calculus teacher was the first one that I saw it from, and he said that he was an atheist, but this was proof there was a God. So I mean, it has this kind of mythic status, like you were saying, the identity. And occasionally there'll be polls that are done, you know, like what is the most beautiful equation in mathematics, and Euler's identity always wins by landslide.
Mm-hmm.
Yeah. Okay, so but you're saying you can get there just using calculus anyways.
Just using Maclaurin series and a bit of trig.
Okay.
So I guess the first there are 3 things you kind of need to know beforehand, and they're just the Maclaurin series for e to the x, sine of x, and cosine of x.
Okay.
So e to the x, the Maclaurin series for that is, I never remember it, but the sum from 0 to infinity of x to the n over n factorial. The Maclaurin for sine of x is again the sum from 0 to infinity of -1 to the n over 2n plus 1 factorial times x to 2n plus 1. And then the last one, cosine of x. We're in a library. I should probably speak a little quieter.
Well, but this is the downstairs where people talk, right?
Ah, true.
Okay.
That one is sum from 0 to infinity, -1 to the n, right? Yeah. Over 2n factorial times x to the 2n.
Okay, and so part of the idea of these series for me is that idea of kind of successive approximations, and that if we take it to infinity, it's no longer an approximation, it's exact.
It's exact.
Right,
Yeah.
so you're writing down that e to the x, featuring this crazy transcendental number e, raised to a power x, so it's a function, is equal to this kind of infinite polynomial. And it's true that those are literally equal. They are. There's different ways to write down that exact same relationship.
Yeah, and that's why I like the Taylor polynomials in the Maclaurin series, because they're reasonably simple, or at least the idea of them are. The idea of them is. Anyway, and you can derive these from more of a from scratch, basically, if you really wanted to, but that takes some time, and they're pretty well proven, so you might as well just look them up on the internet. So yeah, that's the 3 starting points.
Okay, so so Euler was particularly famous for using these series, right? So now we've named this identity after him. He didn't name it after himself.
Yeah, because he doesn't have enough named after himself.
Well, actually, it was a problem. There was a principle at one point that you name things after the second person to work on them after Euler. because at one point, more than half of the math that was known had been proved directly by Euler. So they needed some other kind of naming convention. But this one was important enough, they thought, no, this we have to name.
This we have to give to him.
Anyhow, so he used these series all the time. And he's the one who's kind of tightened up the rules for how we use them. So, like, when is it okay to add them, subtract them, do these kinds of things with the series.
I did not know that, actually. It's interesting. Alrighty. So, with the sine and the cosine, when you write them out, you kind of see this these little jumps. So where cosine has all the even exponents, you know, x to the x squared, x to the fourth, x to the sixth. Sine has x cubed, x to the fifth, x to the seventh, and so they kind of flip flop between those things. And when you have e to the x, it has just all of them. So you can kind of see a bit of a similarity between them. And then this is kind of where you need to have like previous knowledge of how to prove this. Like you probably wouldn't think of this just on your own, but if you take cosine of x plus I times the sine of x, and then you write that out in the polynomial form of it, it's a bit exhausting.
Seems like it takes forever.
I proved it the other day, and it took me like 5 or 7 minutes just to like write out all the terms of it, because they're a bit bulky.
Okay, so I'll put the terms up in the video.
All right.
But what's the idea? What makes it work out? Because obviously we're going to have a real part that's all those even powers from the cosine, and then we're going to have the odd part, which is imaginary with all the odd powers from the sine.
That's right. And what makes that work out is when you raise e to the ix instead of e to the x, and essentially in all the in the terms of its Maclaurin, you just replace x with ix, and then when you multiply that through, you get a positive part and a real part and a complex part. So it.
So could we see a couple of those terms? Because
Yeah.
I feel like that's kind of where the crux of the matter is, right?
All right. So.
And the reason we can put e to the ix is e to the x that's just a function, right? Saying the x is literally a placeholder for what we want to put in. So Euler realizes that, oh, well, we can put anything in there, right?
Yeah.
And that kind of thinking is what led him to extend mathematics from the real numbers to the complex numbers. He had a very robust understanding of how complex numbers worked. And a lot of it was funneled through this e to the x series, because it's somehow so elemental. It's like the polynomial and the factorials. There's something just kind of heart of nature about it.
Yeah, it is. It is something it's cool to explore all the connections there.
Yeah.
So I'm writing out a couple terms in each series, just to get kind of a visual standing for me.
Okay.
Because I find it helps. e to the x, or e to the ix, I'm going to write out a couple extra terms just to kind of show the how it's a combination of both.
Okay.
And I did the math for these earlier, found them out myself. You can check them if you want.
Okay, so before we had all positive terms, and now this e to the ix looks like an alternating series.
Yep.
But not a traditional alternating series where it goes negative, positive, negative, positive.
Right, because it's got the imaginary part, so it has kind of a stalling to it almost. I don't know, I'm imagining like a car engine or something where there's just this weird like break because you've got a positive real, and then you've got a positive imaginary, and then you've got a negative real, and then you've got a negative imaginary, and then you've got a positive real and a positive imaginary, and on and on. So it takes into account both, I guess, of both parts of that.
Mm-hmm. So one way that we talk about multiplication by the complex numbers is as rotation. Have you ever seen that?
Yeah, yep.
Yeah, so with I, because I has magnitude 1, we can think about it as just kind of rotating around the circle, right? Like I to the 0 is 1, right? I multiplied by I, so it rotates 90 degrees.
You get a positive imaginary.
Yeah, and then you rotate it 90 degrees again, negative real, another 90 degrees, and it's negative imaginary.
Yeah, those intuitive ways of thinking about things are really great. They really help you out, especially in higher mathematics.
Okay.
So from here, you see there's this 1 and negative x squared over 2 and positive x to the 4th over 24, which you see are the first 3 terms of this, which goes on forever. And then you also see I to the x, negative ix cubed over 6, and ix to the 5th over 120, which you see are all in here, and they're all up here. So it's a pretty good intuitive proof, I guess, that these are just, when you add these two together, you get this. So that, essentially, all that goes to prove that e to the ix equals cosine x plus I sine of x. And from here, the rest of the proof is pretty simple because you see e to the ix, and we're looking for e to the pi I. So all we have to do is put in pi for x, and we get e to the I pi equals cosine of pi plus I sine of pi. And we know that the sine of pi is 0, and we know the cosine of pi is negative 1. And then to arguably finish the formula, some people like to leave it at this one, you just add 1.
Because that's nice, then you put the 0 in it.
Because then you put the 0 in it.
So now we've got all 5 fundamental numbers
Yep.
in that same equation.
Yep, and that's Euler's formula.
Excellent. So is this something you did in class, or something that you just found interesting and you pursued yourself?
Yeah, I think I watched a video on Numberphile. It's a great channel. It might have been Numberphile. It might have been another one. But it's something that I found almost like controversial. Like I didn't quite believe it at first because I couldn't.
It looks crazy.
It looks crazy, and it looks like it shouldn't be real because you've got like e raised to an imaginary number, and like I haven't learned about that ever. And then like what happens when you raise e to the pi? Like how is that any sort of simple function? But it all kind of plays out into this just really nice formula.
Yeah. And it's one of the things that, those kind of relationships are what helped convince Euler that the complex numbers are the kind of the natural setting for mathematics. Right? So the real number stuff that we're kind of trained on is just a special case. Right? So a lot of these, and so things like even quadratic equations, right, that don't always have real solutions, they always have the complex solutions. And then it turns out every polynomial only has complex solutions. So somehow the complex numbers are enough.
Mm-hmm.
Right?
Yeah.
Anyhow.
I remember when I was in algebra, and on a test once we had to we had to find the solutions of a parabola, and the answer they were looking for is no solutions, and I had a bit of extra time on it, so I found the imaginary ones, and I wrote them down, and I got marked off a couple points.
Yeah, that's not right. Anyhow, but anything else you want people to know about this, or?
I guess there is another way to prove it that I found equally as beautiful on a channel called 3 Blue 1 Brown, I believe.
Mm-hmm.
That one. I always get confused on the colors. Like, is it 3 Blue 1 Brown or is it 3 Brown?
Yeah, I know there must be a significance to the name. But
It's actually it was the chromosomes. The chromosomes that determine the eye color. He had 3 of them that were brown and 1 of them that was blue, and so it led to a little bit of a discoloration, and so he decided to name his channel after that.
Oh, very nice.
Yeah.
The right before our class started, they came out with the Essentials of Calculus. So we've looked at a couple of those videos.
Yeah, that sounds good.
Anyhow, I'm interrupting. You were saying?
Yeah. Well, I mean, kind of both got off on a bit of a sidetrack. But they have they have a lot more intuitive proof of this, where they it kind of help you change your understanding of addition and multiplication and exponentiation, so that you can kind of visualize what this even means. And it's they do a really good job with it.
Oh, good. I'll link that with this. So thanks very much for talking to us.
Yeah, no problem. Thanks for having me, I guess.